Hello everyone, you're very welcome to today's webinar where we'll be taking quite a technical look at one of the new features we introduced in MasterSeries 2021 in our MasterKey Slab design program, the long-awaited calculating of long-term deflections in concrete reinforced slabs, along with the calculation of crack widths as a more secondary issue. But we are going to be focusing today on looking at the deflections and that by and large obviously contributes to the larger part of the body of work and the complexity surrounding this issue. So we are going to take quite a technical look today, and it's going to be a lot of PowerPoint presentation to give you a good technical background and a lesser amount of time spent in looking at the software, because the software itself is relatively straightforward and easy to use. The main thing being you understand the technicality of what is required. I should introduce myself. My name is Martin O'Gara. I am a director with Civil and Structural Computer Services and a lead developer. So I've taken a particular interest in this project myself, and it's certainly been very interesting and to work through and to gain a good bit of knowledge on. Joining me today also is my colleague Barry Miller, who is one of our lead technical support advisors, and Barry has a bit of expertise in this area as well, so he'll be on hand to answer any of your questions. Okay, so we're looking at our MasterKey concrete slab design module and the addition of the feature for the calculation of the long-term deflection primarily. The long-term deflection calculation is a tricky numerical exercise, and it includes many different components such as cracking, creep, shrinkage, and there are also other important factors to consider that you may not otherwise consider when you're just doing a traditional design, putting together loading cases and doing your actual slab reinforcement design. We'll be looking at what the important parameters are, how to set those up, and then how to actually assess the deflection of your slab using deflection check lines, as well as taking a brief look at the crack widths, as I say, but that is a more secondary issue for what we'll be focusing on today. So we can see a little bit of the interface there. Okay, let's talk a little bit about the scope. We have implemented this to the Eurocode, so EN 1992, 2004, and we've just given you a brief outline there of the various parts of the code that deal with deflection-related issues, creep and shrinkage being one of them. The actual calculation of long-term deflection is covered very briefly in Eurocode in section 7.4.3. You've got a page and a half of notes there and about 3 or 4 formula. So the guidance is limited in that regard, and certainly that's where the likes of the Concrete Society technical report number 58 has filled that void and is an excellent publication in terms of delving into the detail of this complex issue or complex calculation method. Not only giving, it's pretty easy to give a brief outline of the technical aspects involved and what the processes should be, which is what we're planning to do in today's webinar. However, it does go into a lot more detail about the influence of the individual parameters, how much influence does the relative humidity have, how much influence does your concrete grade or your amount of reinforcement have. So it does discuss this deflection issue in considerable detail in its 100-page publication. However, you can get a very good overview of the method involved by reviewing certainly the initial chapters of that publication without necessarily having to digest it in its entirety. So don't be scared of that one. It's an excellent publication, and do have a look at it. The crack control part, somewhat separate from the actual deflection and the cracking that occurs in deflection, but we'll cover that in a little bit more detail later on. But the crack control is done directly from the methods given in Eurocode 7.3.4. A few caveats, and that is at the moment we're dealing with the deflections of flat slabs only, So you may have some drop beams or edge beams in your flat slabs, and albeit the deflection of the slab will be carried out. At present, no deflection or long-term crack creep or shrinkage deflection is considered for the beams. This is currently under development, and that's just something for you to be aware of. Another excellent thing just to be aware of from the get-go is it has been long reported and mentioned again in the TR58 publication that although these methods are detailed and they require a lot of information and a lot of computation, it has been recorded through statistical measurements of the real-world deflection of slabs versus those that have been predicted by the calculation methods, that a range of error is that the real-world deflections have been recorded as being 15% greater to 30% less than the calculated values, and that's statistical information taken from various software sources that have implemented long-term deflection methods. It's really important to say that we can't really apply this range of error percentage to any one piece of software, and even us, we don't know what our error is in that regard, because the implementation of this method can vary from software to software. Different people use different approaches to implement, whether it's creep or cracking or shrinkage, and you know, there's certainly there has been known to be variations between softwares, even for the same application of loading and reinforcement and concrete grades, and that's something to be mindful of. Our MasterKey slab design calculation method, we did do considerable validation work on it, and one of the more useful publications in that regard was the BRE Cardington test concrete building, whereby a number of floors and were constructed to different even reinforcement design methods, and the deflections of them were recorded over a period of time under different loading events, and we were able then to do some validation on that. The other key thing to note about that exercise is that a lot of information was known that may not otherwise be known to the designer at design time. Detailed information about the concrete, its properties, and how the properties varied over time, the humidity. So all of that information, with that being closely aligned, we were able to validate our software and achieve a maximum error of 5.9% in that. It's important to note that obviously in real world situations, you certainly won't have the same accuracy or access to the same amount of information about your material, about your environment, potentially even about your precise loading events. So I guess that's why you maybe have a slightly larger range in reality, because of that potential lack of detailed information. Okay, we're going to cover three key areas here in a bit more detail, and that's creep, shrinkage, and cracking. So concrete creep, what is it? Well, it's really the increase in strain over time under constant stress. So if a concrete is subject to a constant force, it's not going to remain static. It's going to continue to, if it's a compressive force, it's going to continue to compress, and the compressive strains will increase over time as the concrete slowly increases in its deflection. So this creep factor is quite a complex thing, but the most convenient way in which it's accounted for in the codes is the calculation of a phi creep modification factor, and then that's simply applied in this formula 7.20 to the 28-day Young's modulus to give you an effective Young's modulus, which can be used then in the numerical calculations to take account of the creep, and it's certainly a very convenient way of doing that. It's worthwhile noting that the creep coefficient is influenced. It is a measurement of a point in time, so this coefficient does vary over time, and at a point in time, you can calculate a creep value for a particular load that is applied at an earlier point in time. So T is the time that you're measuring the deflection and the time that you're calculating the creep for, and T naught is the time that a particular load has been applied. So T minus T naught would represent the duration of the load. The creep coefficient is also influenced by other things like cement type, relative humidity, ambient air temperature, and slab thickness. I suppose the first thing to say is that many of these things are things that possibly you wouldn't have otherwise considered as a designer when you're designing the other aspects, the ultimate limit state aspects of your slab, or even if you were doing traditional span deflection checks. These are things that you wouldn't have given a lot of any consideration to, but they can have a significant effect on the creep coefficient. Just looking then at the fact that the creep is a measurement of a factor related to a particular load at a time T and applied to the structure at a time T naught. At any one time in a structure, particularly in the long term of a structure, the various loading events that are on the structure will not just be from one load, but from a multitude of loads that have started at different times. So to that end, the creep coefficient is not a straightforward calculation, but you effectively have a different creep coefficient for each of the loads that have been applied at different start times. And the TR58 recommends quite a nice methodology for calculating a compound value of Young's modulus for a point in time, which is effectively a modification of the effective modulus for a particular creep factor for a particular load. So we simply have the total load divided by the total of the ratio of the individual load divided by the individual modified effective coefficient to arrive at a final compound creep factor. So that's a really convenient way to deal with the effective creep at a point in time resulting from different load sources that have been applied at different times. So the implementation in the finite element analysis is that these different loadings applied at different times, we call them load event sequence, and we have a simple table where you can pop those in and pop in the loading, its start time, its end time, and the load. For those of you who are familiar with MasterFrame will know that loads are always associated with load groups, so you simply specify the load groups. The quasi-permanent factor and the beta value will come to, because that's relating more to the cracking aspect, and we'll cover that. But quite simply, you can build up this table, and you may have seen diagrams like this if you've considered this issue of slab deflection at any point in the past, and looked at this here and go, well, no, that's a bit off-putting and a bit confusing, but really it just represents the history of the loading that has been applied to your slab and being aware of what the different possible key loading events are, and the fact that you've got the point at which the slab is struck, other key loading events. So once your slab is constructed, there may be an additional slab then that needs to be constructed above your slab, which is then propped off your slab with a bit of back propping to the level below. And that can apply a significant amount of loading at an early age to the slab. You might then get another slab above that again, so two slabs above the one that you're designing. At some point in the future, that slab will be struck, and with two levels of back propping, you're getting a lesser amount of load down to the slab that you're designing. We're going to talk a little bit more about that aspect in later on in the slides as well, about what the slab above and then the second slab above, how those apply the loading and the importance of those. Certainly these loading events may not even be something that you would have considered in the traditional design of your slab, but they do have significant importance, and we'll discuss that a bit more. And you might have some finishes, some partitions, some permanent, your long-term variable loads, and perhaps some frequent loading as well, which would lead into perhaps a frequent load case, which we do cover, both the quasi-permanent and the the frequent load case. So that's the load event sequencing, and that is really important to know that information and to be able to predict an accurate deflection. This E-comp that we looked at in the previous slide is calculated for each finite element at a time t. So effectively, if we just go back a slide, the W value that we mentioned back there, let me just see if I can quickly go back there. 1 second. Let's see. Yeah, here we go. The W value that we mentioned here, in the TR58 publications, it talks about load, but really that's a proportionality of what the force is in the concrete. So it could be force, stress, as long as we're getting the proportions of the loading from the different events. But we then in the finite element implementation, we calculate that force or stress or moment in each finite element for its principal or its two key directions, and we calculate a compound value of Young's modulus for each individual finite element based on the known stresses from the different loading events, which is all taken care of in the background for you. So we can look at that compound creep factor in the software. Our creep coefficient, we call it the creep factor, but you will have a different one of those at each of the different loading event times. The times that you put into your slab loading event sequence will become the times at which we do a full rigorous analysis at every single one of those times, and allowing us then to give you information about the deflection, the cracking, the creep of the slab at each of those key points in time as well. Okay, moving on to cracking then. A couple of major influencing factors. Obviously the reinforcement, primarily the tension reinforcement, albeit both compression and tension reinforcement is considered in the inertia of the slab when considering the distribution of strain and stress and the stiffness of the slab. But in terms of the cracking, obviously it's the tension reinforcement and its cover that has a significant role. Also a significant role is the strength of the concrete, FCTM. Now, the strength of the age is also important, because obviously if we're striking the slab at an early stage, let's say 3 days, 7 days, the concrete won't have achieved its full strength. So it's important for us to include that and account for that at the appropriate time for each of the times that we're doing the analysis for. The code talks about shrinkage restraint as a methodology for dealing with shrinkage restraint. And effectively what that is, we'll talk a little bit more about shrinkage in a later point, but the shrinkage restraint can be input as a percentage, and it directly affects the tensile capacity of the concrete. Where you've got zero restraint to shrinkage, then you can use the full FCTM FL, which is an enhanced value of FCTM that you may be more familiar with. So this potentially could be something between 30 and 40% greater for a typical slab, the FCTM FL and the FCTM. There's a very simple equation for calculating that based on the thickness of the slab. So your shrinkage restraint effectively linearly varies between these two values based on the percentage of restraint. So the more restraint you have against shrinkage, the more actual stress that the shrinkage has the opportunity to produce, and that stress is accounted for by an effective reduction. So when you're at 100% restraint, you're on the lower end of your concrete tensile capacity, and that's how the actual shrinkage restraint is recommended to be implemented. Value of shrinkage restraint, what is the value and how do I know what to put in? Certainly a value of not less than 50% is recommended, and there are publications which we'll talk about in just a moment or two that tell you, what you need to be looking out for in terms of shrinkage restraint. You are putting your finger in there a little bit and saying, okay, well, how much restraint do I expect my surrounding structure to provide to the in-plane membrane action of the slab? If it tries to shrink, is it going to be able to shrink freely, or is there going to be great big shear walls at different parts of the building which will restrain that shrinkage and then in effect produce additional tensile stresses in the concrete, which is effectively what we're doing here by using a reduced tensile strength capacity. Tension stiffening is something you may have heard of around this topic of cracking. That is really the amount of concrete really that is in tension but has not yet ruptured and contributes to the stiffness of the slab. So effectively what we're saying is that at any point in the slab you can go between an uncracked section all the way to a fully cracked section, but you can be anywhere in between. And this is what this distribution coefficient zeta in the code talks about. And you have a direct relationship between the cracking moment, the moment at which the first cracking will appear in the slab, versus the applied moment. And this is where this beta factor comes in that we mentioned in the loading event sequencing table, whereby typically for most types of loads it's 0.5, including the short-term overload like your slab above loads or your striking loads. Those would typically have the value of 0.5. But for single or short-term loads, the values would be 1.0. So effectively that distribution, which is a value of between 1 and 0 effectively, where 1 would mean that the slab is fully cracked and 0 would mean that we're not cracked at all. And that feeds into this really balancing formula between the quantity of property in the slab with its cracked and uncracked. So just as the direct proportion of a certain amount cracked, a certain amount uncracked, and we end up with a final coefficient here. And this coefficient can be applied to really a multitude of different parameters. It could be the curvature or the deflection in that respect, but that's not exactly how we will implement it in the finite element software. It's worthwhile mentioning that once a crack occurs, it remains. So if your early striking or loading of the slab causes the slab to crack, that is permanent and non-recoverable, and will follow the slab through for the entire duration, life cycle of its use. So it's perhaps something we want to avoid by minimizing, by making some good decisions at the early stage with how we load the slab and how early we load the slab. The implementation of the cracking in the finite element analysis, apologies, these are so wordy slides and so much here, but we really want this to be a good reference for you if you want to look at the technical aspects of this at some point in the future. We looked at the alpha coefficient previously and how that was applicable to the deflection or curvature in the slab, but in terms of the finite element analysis, it's much more convenient to apply that with a bit of modification naturally to the stiffness of the slab. So the stiffness of the slab is changed to be partially cracked or partially to swing between fully cracked and uncracked, and that is assessed at every single finite element in the slab for each of the principal directions of force. So the force is rotated into the principal maximum directions, along with the reinforcement. The properties of the slab assessed, the check for cracking carried out, and the stiffness modification made in those axes, and everything transformed back to the appropriate stiffness for the individual finite element. Worthwhile noting that the effects of axial force are included, which isn't something that's always included, and this is, I guess, where I mentioned previously that from software to software you might get different implementations and different results. The effect of axial force we felt was just too significant not to include and to account for. So the in-plane membrane action of a slab can be significant because it is acting as a diaphragm in your slab to transfer your lateral forces through to your shear cores and things like that. And it will have a significant part to play in whether what stage your slab cracks at, and how much it cracks, and even the effect of that on the likes of shrinkage and other things like that, and also crack width calculation. So that is fully included there. The other thing about cracking that makes it quite a challenge is that as your slab cracks, it will lead to significant redistribution of forces in your slab, which will then lead to further crack, which you might think of as a propagation of a crack. So that leads to a non-linear iterative analysis, and a lot of time and effort has been taken to optimize that and make that as numerically optimized as possible, because that's certainly where the bulk of the analytical time goes towards, that iterative analysis leading to a converged situation that we can then get a result from. At each time t that we consider the analysis at, the maximum crack ratio in each element from the previous time is observed. So this is back to what I was said in the previous slide, that once a crack occurs, it doesn't close up again. Well, it may close up, but it doesn't recover its stiffness. So the actual extent of the crack and how much of the slab is cracked has to be observed and brought forward, and it may be increased in another loading event, but it certainly can't reduce or be minimized once it has occurred. The load term beta in each finite element is calculated as well as a compound value in the same way that ecomp is calculated, and that's maybe not something that's very clear in the way that it's talked about even in TR58, but the beta factor is a factor that's relative to each load, and at a point in time you have a multitude of loads, so therefore it's not appropriate to apply a single beta factor at a point in time, but it's really a compound beta factor from your various different loads and the proportions of them in terms of the force that they exert on each individual finite element. We also in the software give you the maximum distribution coefficient, so the zeta value, what we call the crack ratio. We can give you that to you as a contour output with positive and negative values for sagging and hogging areas of the slab. Also, the direction of the crack is important in that you can see that in the software, and you'll get grey lines in the finite element indicating the direction of the crack, and you can look at the cracks in two orthogonal directions to get the extent of the cracking in the two principal axes of the slab, or the two principal axes of each individual finite element, to be more precise. We talked about the loading event sequencing and how applying load to the slab at the early stage was something that we should consider. And there's been a lot of research over the years surrounding this topic, and it's called early age loading. And I guess the thing about it is that you're applying loads at a time to the slab when it hasn't reached its full capacity, its full 28-day capacity. And you may strike a slab with increased pressures on construction speed. A slab may be struck as little as 2 days. In accordance with the code and the modification of the tensile strength with regard to the age of the concrete, you're down at 50% of the strength of the tensile strength of the concrete at that 2 days versus the 28 days. So, and the self-weight of the slab isn't insignificant, it is quite significant. So that could certainly produce a level of stress in your concrete that you would not otherwise have considered in your normal serviceability design, at the final long-term stage. One of the other loadings is apply at the stage of your construction load. Thankfully, your construction load is generally pretty small in comparison to the slab self-weight. However, another significant early stage loading is when you then start to cast slabs above. So if we consider this slab here being the slab that we're interested in, another slab might be cast above, and this is what we call the backpropping down to the slab that was previously cast below. So this is the slab that's been poured. This is our slab that's been poured and cast and is now firming up, and certainly in the BRE Cardington building, the slab above was poured at day 12, from day 12 to 14. And that obviously 100% of the load from this slab resulted in 70% of the load coming down to this slab and 30% coming down to this slab. You may think that it should be 50-50, but because of the elastic shortening of the props, it's not a straightforward distribution that you get more of the load onto the higher level. Certainly it's possible then that you would do a second level of back propping down below here to further distribute that. However, it maybe doesn't have as big an impact as you might think. You maybe reduce from 70% to 65%. I'm going to give you a reference to where you'll find a bit of information about that in a moment or two. The thing about the construction stage loading and the slab above loading is that this could be one of the most significant loading events that your slab experiences at a time when it hasn't developed its full strength. Certainly at day 12, we're still only talking 85% of the full 28-day strength. And as well as that, these are events that we perhaps haven't considered in the design, or we would have otherwise thought about in the design. But early stage cracking could occur, which again, as I say, is non-recoverable and will impact the stiffness of the slab quite significantly over to its long term. So it's something that you want to try and be mindful of and try and minimize to get around that. The effective early age loading is very much also to be considered alongside what the final stage loading of the slab is. I mean, certainly if you're loading the slab with a load that is greater at 12 days than the final load and you haven't achieved your full strength, then that's going to be the most significant load event in terms of cracking that the slab is going to experience, perhaps way in excess of what would be at its final stage with perhaps a greater load, but with the concrete then having achieved its full strength. So that's just something to be very, very mindful of, and is worth paying a bit of attention to. Concrete shrinkage, we obviously is more significant than you might initially give it credit for. So we're talking about drying shrinkage and autogenous shrinkage, which is obviously drying shrinkage is loss of moisture, and the other autogenous shrinkage is the chemical reaction of the water hydrating with the cement, causing volumetric changes in the material through that chemical process. Both are simply added together to come up with a final shrinkage strain. And again, this is something that develops over time. So as the slab continues to dry out and to hydrate, that shrinkage strain will increase, but eventually taper off to a constant value. It's influenced by concrete grade, cement type, humidity, and also slab depth, because obviously the more exposed surface area of your concrete versus the volume of the concrete, the more drying shrinkage you're going to experience, certainly anyway. The thing about shrinkage is that if you had equal quantities of reinforcement top and bottom, it actually wouldn't be a major problem for your deflection, because your whole section would shrink uniformly. But where you've got different quantities of reinforcement at the top and bottom, which you most certainly will have, that then you have the shrinkage of the concrete. So the centroid of the concrete will produce a shrinkage strain multiplied by the modulus of the concrete, will give you a shrinkage force, and that force will be applied at the centroid of the concrete material, which is offset then from the centroid of the overall section, which then simply produces a moment induced in the section. And that moment certainly will be of a sign that exacerbates the normal deflection. So it will be nearly always in addition to the normal deflection of the slab, and can contribute as much as 25% to your overall deflection, where your tension or your compression reinforcement is significantly less than your tension. So it creates a little bit of a reverse situation in that obviously increasing your tension reinforcement will have a beneficial effect in terms of reducing cracking and also increasing the inertia of the slab to a lesser extent. But it will have the opposite effect in shrinkage if you increase the tension reinforcement without also increasing the reinforcement on the compression side. And that's something we've observed ourselves in some of our own analyses, and it creates a little bit of an unexpected result in certain circumstances once you've increased the reinforcement and you don't get the same effect that you might have appreciated. So in terms of its implementation of the software, again, I know many softwares approach this in different ways, but we effectively do this through a rigorous application of the shrinkage strains, producing an equivalent moment, and those moments are applied post cracking and creep at a point in time to the slab to produce an accurate set of deflections which match the shrinkage strain that's predicted. It's worthwhile noting as well that the shrinkage strain is also subject to the distribution coefficient rules with regards to if the finite element is partially cracked, then the shrinkage strain, you get a different shrinkage curvature because you have a different section property between a cracked and an uncracked section, so you can vary between those to arrive at a final shrinkage curvature, and we do fully implement that approach. As I said previously, the shrinkage will induce membrane stresses, but that's taken account of through the shrinkage restraint percentage and how that will then interpolate between these two values of tensile capacity. So in terms of evaluating and checking deflection, we obviously will analyze two loading cases, the quasi-permanent case and optionally the frequent loading case. It's worthwhile noting that these are quite separate from the normal MasterFrame loading combinations that you might be familiar with. The deflection analysis is even a separate analysis from your normal analysis, and as it needs to be, because it is quite specialist and its own thing. Deflection checking is done through check lines in terms of applying an acceptance criteria to the deflection. So we can draw multitudes of lines and apply for each one of those lines a variety of criteria. So not just one check criteria, but multiple check criterias. And one of the very useful things is that you can then apply criteria to the difference of deflection between two times, which is something designers would often have a need to do. For instance, you want to know the differential deflection in your slab between the time that you built your partitions and applied your partitions, and then, which might be, say, day 100, but you then want to know what happens in 50 years' time due to creep. Will the differential deflection between the time the partitions were built and a long-term value produce a problem in the serviceability of the partitions? So you often want to know the difference, the deflection that's resulting in the difference between 2 points in time due to the sequence of construction and the effect it would have on certain partitions or other things that are built and applied at different times. Okay, so that's another little shot there of the different criteria that we can apply. So a little bit of recommended reading, as I mentioned before, TR58, really good publication, an excellent publication for a really light, well, not, I would say, covering at certainly an initial level, the vast majority that you need to know about this topic is the concrete centers, how to design concrete structures to Euro Code 2, Section 8 deflection calculations, and it does an excellent job of looking through the various attributes and their importance, and providing really nice flow charts in terms of the approach to the assessment of deflection. It's worthwhile noting a lot of these publications talk about assessing curvature, and then curvature can be integrated to arrive at deflection, but when we're implementing this through a finite element analysis, it's done slightly differently through not curvatures, but modification of material property primarily. With regards to the loading on a slab due to the casting or pouring of slabs above, a really good publication is an article in the Structural Engineer from December 2016, Temporary Works Toolkit Part 4, an introduction to backpropping of slabs. And just one of the key takeaways from this, it talks about different methods in which you can estimate how much of the load from the slab above that's been poured comes down to your slab that's being you're measuring the deflection on. With one level of backpropping, it talks about 70% and 30%. With two levels of backpropping, you know, the 70% doesn't come down that much. It reduces to 65%, but the other levels then share that a little bit more than that. So that's just one of the methods, probably the most common method that people use to estimate their percentages of share of load from slabs being poured above. So a few key takeaways surrounding deflection before I promise you, get into having a quick look at the software and having a look at how this is done. Accurate deflection of calculation requires the detailed planning and knowledge of the slab loading events, and particularly at the early stage of construction. When is the slab going to be struck? When are the slabs above going to be poured, and how long are they going to be there for? These are all things that you know, as designers, we have to think a little bit more about and have more liaison with our contractors to agree on and make that part of our specification, because it certainly can make a significant impact on the final deflections if we get some of these wrong, or we don't stipulate exactly when these key events have to take place. So that's really just leads into like an awareness of the early age loading. And in the software, we allow you to look at the first crack time plots. So you can look at a plot for each element as to what time the first crack appeared at. And if you were getting, you know, widespread cracking occurring when the slab is struck, then that could be something that you might want to revisit in terms of when you want to strike that slab. Planning of the backpropping, how many levels of backpropping are you going to specify, and again, that's part of the specification of your design, and make sure that that is implemented and carried through. Also, more detailed knowledge of your concrete material. Certainly as designers, we don't often think about what our cement type is, or at least at the initial level when we're choosing a basic concrete grade. But it can have a significant impact on both the creep and shrinkage. Relative humidity as well is much more significant in its impact on creep than we perhaps initially realize. Typical values of relative humidity might be 80 to 85% for external exposed environments, whereas maybe 40 to 50% might be typical for the internal. But we would maybe get 20% difference between those two ranges as well in terms of the final deflection. So shrinkage restraint, what value do I use and how important is it? Again, the publication here that I talked about does quite a good job in terms of talking about shrinkage restraint and gives you a couple of examples, and some other publications that look at different layouts of shear walls and core walls, and how you might have a low restraint structure versus a high restraint structure. So that's a good publication to look at to maybe to answer that question a little bit more. The one thing I would say with regard to all of these parameters is really quick and easy to vary those within the software. So if you're not too sure what value of restraint to use and you want to play it safe and use your your full 50% or full 100% restraint, you can change the value of restraint, do a quick analysis, see what the impact and the result has. It could be that if you don't have widespread cracking, that the shrinkage restraint doesn't really matter too much anyway, in one extreme or the other. So it's really easy to do an analysis at a certain strike time and see what your deflections are, see what your first crack age is for each of your elements, change the strike time, do another analysis, and see how much of an impact that makes, and is it worthwhile leaving the slab for another day to reduce the deflections to justify the design. So that's worthwhile saying that you can do that really easy. Crack widths we're going to have a quick look at, as I say, but it is much more less significant in terms of the numerical side of things than the deflections. It's worthwhile noting that the crack widths are calculated purely from the code and are somewhat separate and not related to the cracking ratio that we get when we're assessing the deflection. So you might get lots of cracking occurring in your deflections, which might not necessarily lead to crack width problems when we're assessing the crack width, because it is a slightly different thing. We do tie the two of them together in some sense, and because one of the key things about crack widths is the service stress and the reinforcement and the tension reinforcement, and that is informed by the state of the slab in its deflected form, how much it's cracked, what creep has played a part. So the cracking and the creep certainly play a part in determining the final surface stress in the bars, which then goes on to influence the actual calculation of the crack width. Okay, so we're going to then break from this and have a quick look at the software in the time we have remaining. Looking at my frame load diagram, this is a slab that I have some loading on. So we've got obviously the dead load itself on the slab. We have some partitions in the central zone, and we've got a little bit of construction, 0.75 kilonewtons per meter. And then I've got my loads from the slab above, which is about 4 kilonewtons, the slab directly above, and then the second slab above is a lesser value of 2. And that's the extent of the loading that I have in this here. Perhaps in reality, you say we might have one for services and finishes, and another one for another type of variable load applied at a different time. So it's really worthwhile saying that the slab's already been designed in terms of its reinforcement. You must do that before you go through to do your deflection assessments. So do your initial ultimate limit state reinforcement design using the slab design tools here. But we're just going to go straight into the slab deflection area. Now, we add then a deflection check brief, and this deflection check brief then gets applied to a slab, and not just that slab, but if you select the slab, it will then group together all connected slabs at the same level, because we can't analyze a slab in isolation without considering other FE surfaces that it's connected to, which share load and influence the stiffness. So they are all tied together. So we'll select that slab. Quick look at what we have here. We're saying here, in terms of long-term deflection, that we want to measure long-term deflection at, that's 50 years for us. And our cement type defaulting to R. Our shrinkage restraint is down at the minimum of 50%, which I'm happy enough with this. Few crack width, allowable crack widths, and that's the extent of the parameters there. The more significant parameters are the loading events that we talked about. So let's just build up a little bit of a loading event based on the various loads that we have. So first of all, I want to say what time I'm going to strike the slab at, what time I'm going to remove the formwork, and we're going to say that happens at 3 days. And this is the self weight of the slab in load group D1. And of course, it happens for the life cycle, the entire lifetime of the slab. It's a permanent load, it's not going away. Secondly, I want to apply then some construction load. And this is going to be applied again at the time of 3 days, but only up to a time of 28 days. And I think that was in load group L2. Okay, we'll look at the factors in just a moment. Now let's look at our slab above. Right, I'm going to say that starts at a time of, say, 10 days, but only until a time of 13 days. And that was load group L3. And another slab above that yet again. Just going to ignore that and continue because we're obviously a little bit tight on time, and we're going to go from 25 days to 28 days. And that was L4. And finally, I had some, what I'm going to call partition loads. And I'm going to say that those get applied at day 60 for the life cycle of the structure. And that was L1, which was the partial load in the central bays that we looked at. For the quasi-permanent condition, it's normal to keep the short-term overload values at a factor of 1. But certainly this variable load, I'm going to say, is a quasi-permanent factor of 0.3. Now, it's also possible to include the frequent load case. If we check this, we can then say what the frequent load factors are, but it's important that you then add in a frequent load case. So whatever that might be, a short-term frequent load, we might say it starts at day 200 and ends at day 201, and it's load group L5. But it would be important for me at this stage to say that the frequent load is load group L5, so I identify that as the frequent load group. It wouldn't have a factor in the quasi-permanent, but it would have a factor in the permanent, and that so you might set up something like that. And certainly these, in terms of their beta, might be more like a value of 1 for a long-term load. Certainly that would be still at 0.5 for a short-term load. But I don't have a frequent case, so I'm just going to take that out and delete that last load event out there as well. You can save these to a file and import them from a file to make your job easier for setting up subsequent slabs. Right. And believe it or not, that's the hard part done. Other things with regards to humidity, you can build up a variation in humidity over time as well as temperature. Temperature, obviously, the higher temperatures will assist in the curing of the concrete and lead to a better outcome. But that may very well change over time as the building is perhaps exposed to the elements in the early stage and then clad and at a later stage. So it's even possible, obviously, for the humidity to be an exterior level humidity up until the building is clad, and then a different level of humidity thereafter. And you can build up a profile of that in here simply by adding new humidity and temperature events. Okay, so we're ready to do some analysis now, so let's do that. So what's going to happen now is going to analyze the slab at each of these key loading events. So analyzing when the slab is struck at 3 days, then moving on to then when the first slab above is poured, not just but both at the beginning of that load application and the end of that load application of these different loading events, so that we can see the difference between what happens at the start and end of a loading event. Due to creep, you will get a variation in deflection. And that's that analysis complete. So we can look at some of our contour output that we talked about. These are our deflections. So this is my deflection at strike time. So I've got a deflection of 13 millimeters at the 3 days at this location. So just a quick look through then, as the slab above is poured, maximum deflection of 23 at the beginning of that event, and then at the end of that event, before it's taken off, ever so slight increase due to creep occurring over that 3-day period, which will be obviously quite minimal. Then we've got the second slab above start and end. Then we've got when our partitions are applied. So obviously the slab above events are now removed, and the 60-day event has begun. And then the final event then is the long-term value. So we can see actually the difference between the partitions being applied at 60 days, giving me approximately 20 millimeters, to approximately 24 millimeters all the way to 50 years. So we're getting about a 4 mil value or 4 mil value of creep occurring over that period between 60 and 50 years in the slab. So in terms of assessing those deflections, well, let's move on to look at other contours before we do that. So we have the values of creep. Now it's worthwhile noting that these are the actual values of the creep coefficient. Some softwares present this as the 1 plus the creep coefficient but no, we actually just give you the creep coefficient, not the 1 plus that you have in the denominator of the the way it's applied to the modulus adjustment. So we're seeing values of creep here at the early stages of maximum values of 0.5. But as certainly time increases and we get all the way to the 60 days is quite an interesting one, because we might try say, well, creep certainly isn't a uniform thing, and this demonstrates this, because the values of stress in these internal elements have loading that have been applied to them at all different times, and that this is where the compound creep factor comes into play in terms of how much in each finite element, how much force are there from the different loading events, and how does that balance out to a final creep factor or a compound elastic modulus. So then that as time increases, that levels out some more again. So we're getting a maximum creep coefficient in the long term of around 2. Certainly, as if we were to change the cement type, we would see a reasonable change in that, or change our humidity, which currently is at 50. If we were to increase that to 100, we would see a bit of an impact on that. The creep coefficient certainly would come down. So let's have a look at then how we can assess the deflection. Oh yes, a few final things. We've got this is what you could call the distribution factor, your zeta. We call it a crack ratio. So you do get cracking occurring in 2 orthogonal principal axes. So this is the forces rotated into the principal axes, the reinforcement along with it, and the assessment of cracking is then done in those axes. And you can see quite clearly here the extent of the cracking that's occurring and in 2 principal axes. Time at which first crack occurs. So we're seeing here vast majority of our cracking occurring at 3 days. Could I delay that strike time by another day, and how much of an impact would that have on the extent of cracking? I'd probably still get a lot of cracking occurring at 3 days, but would it be lesser when my crack ratios reduce? Ultimately, what impact is that going to make in my final deflection? Really easy to do that. Quickly go and change your loading event to a different number of days, rerun your analysis, and you get the impact of that decision right in front of you. So 2 different directions. You're seeing a little bit of extra cracking coming at 10 days when the slab above loading is applied, but certainly the vast majority of the beginning of the creep or the crack occurs at strike time at the 3 days. As I say, where your modulus of rupture, your tensile capacity of the material is significantly compromised, from its full 28-day strength. So let's look at assessing some of this deflection. I'm just going to sit here on the deflection at 50 years to give me an idea of the pattern of deflection and where potentially I want to measure deflection at. So certainly I might want to measure deflection up around here. So it's done by using check lines. So a check line is simply a line that you draw between 2 support points typically. So I've just added in a check line, and now I'm going to draw it between 2 points, and that's it drawn in. But it doesn't really do anything until I tell it criteria. So we'll go in and say, right, okay. Again, these can be set up in sets or saved to file and retrieved from file. But I'm going to make one criteria here called long. So this is what I'm going to say is my long-term deflection. And it's not a differential deflection, it's just a deflection at it. When we don't say differential, we don't need to specify an end time. We're just saying I'm measuring deflection at the 50 years using span over 250 and relative to 10s as well. So if we've got elastic shortening in these columns, we don't want those to influence the final total deflection. So there is that. I mean, these contours don't take account. These are the absolute values of deflection. So in a different structure where there's a lot of axial shortening, we might see a little bit of difference between this value and the value that gets extracted from the line. So let's do that. While I'm here, I'm going to add another criteria. I'll call this partition. And I talked earlier about the need to get the differential deflection because we build our partitions at 60 days, but we want to know then what happens at at 50 years, how much difference in deflection occurs over that time, and you can think about your own limit that you want to apply to that. So closing that, we now get deflections of the the 23.62 millimeters at the 50 years. As I say, slightly different than we have here because elastic shortening of columns likely contributing to that. As well as that, this may not pass exactly through the maximum point, so you may decide to draw another line in the other direction and do that. But typically it wouldn't be too far away. But we're getting then a differential deflection of 4 millimeters over the 50 years minus 60 days of differential deflection affecting our partitions. And of course I can then add more of those check lines. Let's just add another one in, and let's draw it in down the bottom here. And again, we'll just use the same criteria that we used the last time, and then we're getting the check coming in from them. You can grab them and move them around. You can put them to different places, so they are clickable and draggable. It's also worth bearing in mind there in the check criteria, if I had a cantilever here, I can draw a check line from the support point of the cantilever to the free end and say that it is a cantilever deflection, and then it obviously will know to measure the cantilever deflection and not the in-span deflection when it's doing its deflection estimates there, or deflection measurements. So at the end of the day, really easy to use in terms of extracting out what you need and what you want. The final thing then is to look at is the crack width, and again a few contours surrounding that. And we have crack widths which are really busy values assessed at 4 internal points, 4 internal Gauss points at every single finite element, which you might say is a bit overkill, but why not? So we can see the variation in those, but then the unity ratio is actually quite useful because you can look at this and go, okay, well, do we have anywhere where it's greater than 1? And certainly in one of the principal directions, nothing. In the other principal direction, we're getting a few points where the crack width is a little bit of a problem, and we can see that boiling through in the bottom crack width calculations. At these points, maybe that we accept that and we're not too worried about what goes on around the corners in terms of these crack widths. Maybe a little bit more of an issue there, but certainly we can follow that through all the calculations and see that everything is being observed in relation to that section of the Eurocode. But certainly a much lesser, more empirical, quick set of calculations when compared to the deflection calculations. As I say, the actual service stress that you get is in some way related to the stiffness of the slab and how much is cracked, and that all leads through to how much stress is in your reinforcement for calculating the crack widths. Okay, that brings us to the end of this. We hope you've learned something. This has been quite a technical webinar, and we hope you find this a really useful resource going forward. But it just remains for me to say thank you very much for attending today's webinar. Hope you've enjoyed it, and we would welcome any further questions you have. If you're interested in the MasterKey slab design module and would like to look at that, we're really looking at an aspect of this today. Of course, you've got the whole other ultimate limit state reinforcement design side of it, being the other initial half of this or side of it. So it's a really excellent piece of software. If you are a MasterFrame user, and certainly if you've used MasterFrame finite element analysis, the step to MasterKey slab design will make things really easy for you. So we'd love to hear from you if you would like to consider exploring this a little bit more for maybe even one of your applications. Our sales guys would really love to chat to you about that. But it just remains for me to say thank you again, and we look forward to seeing you at the next webinar.